from Nepal, and he is trained as an engineer when he was in Nepal. And then subsequently, he did his master's in Korea. Subsequently, Sher did his master's in Korea, and while he was in Korea, he was working with professors over there on projects that were dealing with water-sensitive urban design. And for his projects, he was involved in designing this infrastructure to be implemented in Korea. So that was the field version of his knowledge base on this topic. And then subsequently, he returned to Nepal and worked there for a few years as a teacher, actually, as a lecturer in their local universities and colleges. But then he decided that, okay, it's time to upskill. So he applied to come to do his studies, his PhD studies here at JCU. And for his PhD topic, he will be doing slightly different things. So he will now put his focus more on modeling, looking at the impacts of water-sensitive urban design practices in flood mitigation for cans. So it's pretty important because when it rains a lot here, and if you get high tides, then we are at a very high risk of flooding. So hence, Sher's project is really relevant, and he's actually working with Cairns Regional Council and the traditional owners for his project. So let me give the stage to Sher so he can tell you more about his knowledge and experiences in this topic. Over to you, Sher.
Thank you, Dr. Hansi. Good afternoon, everyone. Nice to have you here. Today, I'll be mainly use this platform as an introductory session to introduce my topic on water-sensitive urban design practices, the nexus of field and modeling knowledge. I would like to first introduce my presentation outline as a background, and then I'll be talking my past work related to the field-based knowledge related to water-sensitive urban design techniques, and then what I'm currently doing on the model-based approach. And then definitely I would love to talk in detail about the modeling approach in later talks. So yeah, this is my outline. When we mainly talk about these water-sensitive urban design techniques or water suits, that's typically, we can hear that terminology quite here in Australia. And then they do have these different objectives in terms of how these water suit are, why water suit are practiced. We can see different objectives here. The first one is to manage water balance, how this hydrological cycle operates, and how we can manage those water balances. And then the next will be much more focused on the quality perspective. Yeah, and then the third one will be, third one will more focus on the water conservation, and then the environmental and the recreational opportunities as well. It's a broader perspective how we can manage water and how we can use these techniques to manage those waters. But we can hear other different terminologies which are much more relevant to these water suits, because we can, when we go to the North American side, we can hear the terminology low impact development technologies or low impact urban design and developments. These are the terminologies that quite often used in those parts. And then, but each of these terminologies have their own principles or scope defined depending on their local condition. So when we see this list, we can see the different, in UK, we can say it as a suit or a sustainable urban drainage, or in China, it says as a sponge city. So, but their purpose and then the objective are different depending on their local condition as well. When we see the evolution of these terminologies, first we can see this evolution as a specific technology to perform the specific objective. We can see here at the low bottom here, the first these technologies were much more focused on stormwater management or stormwater control. But when we go with this upper end right hand corner, we can see the water sensitive cities. Like these are much more broader. They have much more broader principles, as well as they try to cover the whole urban water management cycle as well. So we can somehow somewhere listen the water sensitive cities and water should often use interchanging, but they do have these different principles. They do have somehow difference in the principles. So uh, that's why what we are trying to use is we are trying to much more, but for now we are trying to much more focused on the stormwater control or flood control, because when we try to cover all the broad principle, then it will be too much for to discuss. And in terms of application also, we can see the first in around 1960, they were much more focused to have that stormwater control and flood mitigation. But when it comes to 2013, we can see different principles like flood mitigation, recreation, and then pollution control, and many more. We can see different objectives. That's why, but for now, I'll be much more talking on stormwater management and the flood mitigation. So to talk that, what we have to know first is what we are currently doing at our urban area. When we see this particular this picture at this left hand side, we can see our natural land surface, where this transpiration from the plants and then the evaporation from the grounds, and then when there is a precipitation, we can see much more infiltration values, and then the surface runoff is quite low. But when we gradually do this urbanization, when we increase this imperviousness surface, then we can see quite significant rise in this surface runoff, and then gradually significant decrease in the infiltration, and then rise in this evaporation, but transpiration is slightly low. So at that condition, what we are doing is we are trying to control this surface runoff, the runoff generated from the urban area. What we have been doing is we have been using this gray approach or gray infrastructure, which we can see in our roadsides or at our households or everywhere. Like when we just travel to our urban area, these gray approach are much more focused at collecting the runoff from particular sources, and then they are much more focused to transport that to the downstream side or the water, like nearby water bodies. They are used as a transportation medium. So what we can say is we can see the quite significant amount of water at the downstream side when there is rainfall. When there is rainfall, then we can see quite good amount of runoff at the downstream side, because what we have installed this gray approach. We just collect. Yeah, we can see just the picture. We have this. We can see we have much more. Like we are much more trying to improve this ground surface and everything, and then definitely we do have that so much lob with the concrete surface. So we have concretization is quite significant in our urban area. And then this is the roof runoff, which is directly connected to the gutter of our household rooftop area, and then that's directly discharged into the roadside area. We can see the roadside runoff. That's some of them are discharged from this. When there is a precipitation, then some of them are discharged from the roadside as well as from the roof. And then also we have modified our land structure so much. So when there is rainfall, then we can also see the runoff from the previous lands or the open spaces as well. All these runoff are collected here at these inlets, or we can say there are different types of inlet, but we can say as an inlet, this is the point where everything goes. And then we use these underground pipe networks, which transport the runoff from one place to another, like from upstream to downstream, or south to north, or different place. We can see this runoff transportation, like runoff collected from the upstream side to the downstream side, and then crossing this road network. Uh, yeah, we can sometimes experience flooding at these points as well, where if there is any clogging, or if there is any woods or like a leaves and everything, then there might be flooding at that particular location. So yeah, we do have these different channels, and then these online canals as well. The cities like Cairns do have these online canals, and then these concrete channels. We can see these generally at the downstream side. We can see quite a good amount of rainfall runoff collected, because the terrain here is really flat. So the velocity of transporting that runoff is quite low as well, and then that's why it's keep on sagging at a place, and then which slightly covers the surrounding land as well. So if that's the case with the gray measures, then what we try to do in our water suit measures, then in terms of when we try to implement the water suit in our urban area, we are focused. We try as much as possible to harvest those runoff, and then that could be at our household, or that could be at our roadside, because we can implement those techniques at small scale to larger scale. Yeah, because we can implement these techniques at small places as well as at our houses. We can, for example, we can just implement our rainwater tank in our house, just to collect the surface runoff from our rooftop, which we can use that runoff while irrigating our gardens or lawns. So that could be, and then we can even build the larger scale of these techniques. I'll just show you the picture. We can see this is the typical green roof, which tries to retain the runoff, the rainfall. When there is a rainfall, it tries to retain the runoff, and then to gradually discharge the flow into the ground. And then we can like connect these systems to behave as a transporting medium, as well as try to retain them as well. Because what we have seen with the gray measure is they just collect and then transport, but here they collect and then they try to infiltrate or evaporate, transpirate from at the source, and then they also try to infiltrate or retain or detain the runoff when we are still transporting those runoff. So the amount of water received at the downstream water side is significantly low compared to what we have seen in the gray approach. So these are these typical examples that has been implemented. This is an infiltration garden implemented as a roadside, and then we can see these permeable pavements. These permeable pavements are used in our parking lot areas, where we can use these techniques to infiltrate everything whenever there is rainfall. It seems like a concrete, but it behaves as an infiltration medium. Yeah, so and then there are bioretention, and then there is tree box filters. Yeah, yeah. So maybe the earlier picture that we concretize everything on the base of these trees. Yeah, maybe we can just modify simple approach and then improve this infiltration the surface area, open surface area, to soak that water into the ground. So this is the introductory part, what the suit actually is trying to do in terms of stormwater management and flood mitigation. I do have a field-based few slides, which I did, which I was involved during my master's research. And then this is a typical bioretention system which was installed in South Korea, where we have replaced these inlets with this bioretention system. So So this bioretention system will collect the runoff from the roadside and then tries to infiltrate, retain, detain, and then do the process, different processes, and then help to mitigate the runoff. So and then we do have different water source techniques implemented within our university. So we were responsible to monitor those systems. Every rainfall days, we have to be let's say for half an hour or 1 hour before at the site, and then we'll be involved. 3 or 4 people will be involved to monitor this at the inlet points, outlet points, so that how this system works. And then we were collecting these medias, and then also with the plants and everything, how which plant have good characteristics in terms of the evapotranspiration or holding the water, and also the media also. So these are the sites which was within the university, and then we were monitoring this site. And then based on this knowledge, these systems were replicated in the other part of South Korea as well. So which I showed in my earlier PPT. In terms of when I see, we can see the graph here. I have presented the volume reduction and the peak volume reduction here. We can see the good amount of volume reduction with this bioretention, and then the rain garden, and then the infiltration planter, whereas we can see similar type of result with the peak volume reduction. Here we were trying to talk with the peak volume reduction, because when we think about the flooding, then at that moment we definitely have to think what was the peak runoff at that moment. So I have included this peak volume reduction as well. But we can see these small wetlands which have really a low volume reduction as well as a peak flow reduction, because this what we saw that is the rainfall, the performance of these systems were really dictated by so many factors. One of them was definitely the processes involved within that technique, because these two wetlands were just a retention basin. They didn't have that infiltration mechanism, so that's why they were like really low performing at a higher when there is a higher rainfall depth or a higher rainfall intensity. So that was that's why we can see really low values with the wetlands. And the hydrological, we can see this hydrological effect. I have just tried to include the event based. This is the result of a particular event, where we can see the retention and then the infiltration mechanism at the early stage was quite significant, and which gradually decreases as time passes. And then, but in case of wetland, this process is also quite fluctuating or changing. So that's why we do have different. Definitely, when we see this graph, then we do have different questions arise in our mind, which I will try to discuss in my later slide. And then, and in terms of water quality effect as well, we can see this, the first runoff collected at the inlets, and then the runoff collected at the outlet points. When we talk about the water quality perspective with respect to the stormwater management, then there is a terminology quite famous, first flush phenomenon, because in early hours, when there will be quite significant amount of pollutant at our parking lots or roads or our infrastructure, and then when the rainfall goes by, then it will gradually decrease, and then we can see that phenomenon here. And but when this runoff passes through this bioretention system, this is the runoff collected at the outlet points. We can see a good picture at these moments, and then definitely we can conclude that water sources are good in terms of water quality as well. improving water quality as well. So from the field-based knowledge, what we can say is we can see the different conclusion from the field-based knowledge, and then that conclusion has different definitely they do have a different questions as well, in terms of if these water suit are good enough when there is a big amount of rainfall, or when there is a high intensity rainfall, then are they good enough to perform at that condition? Or what if they perform in a different climatic condition? Maybe the South Korean climatic condition was different, and then what we see here is a different climatic condition. So what sort of performance we can see when they are replicated in a different climatic condition? So that those were the few questions is still unanswered, and then we were trying to that's the idea when we come up with my PhD research. We try to replicate that knowledge in the tropical condition. So if we practice the system in a tropics, then what will be the result? And then when we try to go through with the literature, we can see there were few number of literature which were talking about this practice in the tropical region. And then definitely so that's why we try to do, okay, let's use this model based approach and then try to answer these questions. So when I talk about this flooding in tropics, then definitely the numbers the numbers are quite these numbers are quite scary, but at the moment we are definitely experiencing this day on day. So because when we see this, since 1985 to 2015, the total at the global scale, what we can see is there were more than 4,000 flooding events, and then half of them were much more concentrated in the tropical region. And then after 2000, the flooding in tropical region it has increased by 4 times. So that's the quite that's the number that you have to think, okay, what if this ratio continues in the future days? Then what we have to think our urban planning, or think our planning, or our flood mitigation measures. So that's why what we did is we try to and then in terms of duration also we can see the numbers as well. So what we try to do is we try to use this model based approach, and then we can see these different models here available at the market. Some of them are public, some of them are commercial, which can model this performance of water suits. So but at the moment we have been using this Mike Plus, which was started in 1983, and then this model has advantage over other models, because this can do both hydrological and hydraulic simulation at the time, and then also we can introduce the water suit techniques in our modeling practice, and then see how this system performs. I mean, how these techniques will help us to manage the runoff from our urban area. So using that model, we have tried to answer our 3 research questions. The first will be how this climate change has actually impacted our tropical urban flooding. And then the next one is if we implement water suit, or if we have this current scenario, current gray measures, then what would be the difference, or what would be the extent that water suit will be effective in terms of flood mitigation. And then at the end, what we are trying to do is we are trying to include this risk and robustness as a multi-criteria analysis to make a decision making in terms of how we implement water suit in a tropical region. So we'll be mainly focused on these questions, but and then this will be the methodology what we'll be following. But what we can see is when there is a extreme runoff condition, then how we can how this water suit will perform, or how this water suit will be, are they effective enough? And then when we see the cities like Keynes, especially they do have this limited space, and then we are having and then retrofitting these limited space is quite challenging part in terms of economy, as well as in terms of space availability and everything. So in that case, uh, we are trying to rethink, okay, what would be the challenge when we try to retrofit our cities such as Keynes. And then another part is, what if this water suit implemented in this current scenario, they would not perform in the future different climatic scenario. So that's why we are trying to use this RCP 4.5 and RCP 8.5 as a climatic scenario to test our water suit performance in terms of the current city. And then yeah, definitely, as I have told, yeah, we'll be using this multi-criteria optimization approach to make the decision making improvement, how we can improve the decision making, and then compare those results and yeah, see the results, how they go. So that's why what we have done is we have chosen 4 sites within this saltwater creek. This saltwater creek lies within this Kent city, and then this is the saltwater creek stream. You can see here, this is the stream just behind this airport. You can see the board. And then we have selected 4 different locations within that Kent saltwater creek. The first one is the Las Davis Park. This is the most low-lying area where the different factors of flooding, like we'll be seeing different factors such as the upstream flow as well as the tidal flow, and the terrain is really flat and it's just nearby the ocean. At those conditions, how this water suit is going to perform. So we are going to test that one. And then the second one is this IGS Piconis in that's the really a commercial area, highly commercial area. And then we can see lots of almost 95% of impervious land in those conditions. And then the third one is this sewer pumping station. We say it as a Jensen Street Park. That's nearby Jensen Street Park. This is the transition in between the higher elevated area and then and also with the flat lands. We can just it's a place where the elevation transit drastically. So at that place, how we are how this water suit is going to behave. So it's just here we can see that's just behind this IGS Manunda. And then the fourth site is the Engineers Park. It's quite in the elevation, just behind this White Rock State School. This place has a higher elevation compared to the other place, and then low tidal effect. So at the moment, what we are trying to do is we are trying to collect as much as information that we have here available. So we have already collected the DEM data, the latest DEM data from the council, and then the climatic information such as IFT data, and then also the rainfall, and then the temporal pattern, as well as the climatic scenarios from the Queensland future climate dashboard. Most of these data are free. But this is the DM data was provided by the Keynes Regional Council. So they have been really cooperative with providing other data as well, with the drainage data or the other built up areas, and then the road networks data and everything. So that has been quite helpful to progress the work. So besides with the modeling data collection and then working with that, we have also installed the sensors at our project sites. This one is the sensor installed at Engineers Park drainage. And then this is the sensor installed at the Jensen Street. This has been collecting information, the flow from since 2018. So I think we don't have a problem with the model calibrating and everything. But definitely we have already started to collect the runoff condition from Engineers Park 3 or 4 almost from the December this year. So yeah, this is the Engineers Park. Yeah, quite here, slightly at the higher elevation, and then this is our Jensen Street Park, and then there will be our IGS, and then somewhere here the last Abyss Park will by. So that's the progress what we have done, and then with the modeling progress also. We have already worked with the hydrological modeling. So we have used this RORB hydrological model from Monash University, which is giving us this peak flow and then the critical duration in terms of flooding, how peak the flow is from that particular catchment. This is a typical example of a setup in a RORB hydrological model. And then we have already worked in terms of progress with the hydrodynamic setup as well. So we do have this built up area, and then these that's the internal feature that we input in our model, and then the stream networks, and then this black are the pipe networks. And then we have already meshed like work with this grid with our model, and then we have already done this coupling, 1D and 2D coupling, because the pipe network and then the stream flow will be a 1D, one-dimensional flow, and then the overland flow from the ground will be a two-dimensional flow. So that's already coupled, and then now we'll be proceeding how the water soot or the current stormwater, the gray measures will from in terms of current climatic scenario and then the future climatic scenario as well. So concluding, what we can say is definitely when we see with the result from the field, we can see good numbers of volume reduction and then the runoff quality improvement. But at the same time, what we have to think is the performance of these water sources are really impacted by the local hydrological condition or the hydrology of that particular area, and then the imperviousness surface at that location. And then also we have to rethink with the techniques what we have been using, and then the process involved within those techniques, and then the selection of plants or the media, the location we have been implementing those techniques. There will be so many factors controlling their performance. So that's why what we are trying to do is we are trying to foresee that scenario using this model-based approach, and then have that knowledge. Okay, if this is the condition, if this is the scenario, then this might be the result, or this we can see this kind of performance at that moment. What we can do, or do we have to combine different water sources, or do we have to combine them with the current gray approach, or do we have to rethink with the stormwater management rather than directly transposing the runoff from our roof to the roadside area, or do we have to disconnect those systems? That could be the different answer that we can answer from our modeling result. So these are the references. I would like to acknowledge all the people who are here, and then definitely the people who have involved in this process. So definitely the TESS community, and then Dr. Yoko, I'd like to thank for this opportunity, and then definitely the people who have been here listening me. And then at the last, I have this picture from our JCU Ideas Lab. We have a bioretention system over there, and then this bioretention system has been installed to manage the runoff, and then generated from that Ideas Lab. And then maybe we can some days, see those system and then discuss because I think there are people from the plant, the people are plant from who are interested in the plants and everything. Definitely, we can do this discussion or the collaboration and everything in terms of plant selection as well, or the media selection as well. So yeah, maybe we will have more number of these systems installed in our university, so that this could be a showcase, or this could be as an open research site in terms of what we are implementing water suit in the tropics. So thank you for listening. Yeah, thank you.